3D printing in medicine. Module 3, Lesson 2, Tips for CAD design and drawings in 3D printing for biomedical applications. Introduction. Building on CAD basics. In Lesson 1, we introduced the fundamentals of CAD modeling, focusing on workflows, tools, and their importance in creating 3D printable designs. In this lesson, we expand on those concepts, providing practical tips for optimizing CAD design specifically for biomedical applications. Designing for 3D printing in healthcare requires precision, functionality, and compliance with strict standards. These tips will help ensure your models are both effective and efficient for use in medical settings. Understand your printing process. Each 3D printing technology has unique capabilities and limitations. Understanding the specific printer and material you'll use is essential for effective CAD design. 1.1 Resolution considerations. Layer height determines the detail and smoothness of the printed object. Smaller layer heights offer finer resolution but increase print time. Curve and detail handling. Curved surfaces and small features must align with the printer's resolution to avoid distortion. 1.2 Material behavior. Biocompatible materials. Materials like PEEK, resin, or nylon have specific tolerances for heat and mechanical stress. Ensure the design accommodates these properties. Shrinkage and warping. Some materials may deform during printing or cooling. Account for these behaviors in your design. Design with supports in mind. Many 3D printing processes require supports for overhangs or complex geometries. Thoughtful design can minimize the need for supports, saving material and reducing post-processing. 2.1 Angle awareness. Overhangs greater than 45 degrees typically require supports. Avoid these angles unless necessary. 2.2 Support minimization. Add chamfers, angled edges, or fillets, rounded edges, to reduce the need for supports. Adjust the geometry to avoid sharp transitions or unsupported areas. 2.3 Placement strategy. If supports are unavoidable, position them in non-critical areas where post-processing won't affect functionality or appearance. Maintain proper wall thickness. Wall thickness is critical for both functionality and durability. 3.1 Minimum thickness. Thin walls risk warping, cracking, or breaking. Refer to the printer's material guidelines for recommended thicknesses. 3.2 Biomedical applications. Tools and implants require walls robust enough to handle stress but not so thick that they increase material cost or weight unnecessarily. Use fillets and chamfers for strength. Sharp edges create stress concentrations, increasing the likelihood of part failure. Smooth transitions improve stress distribution and print quality. 4.1 Fillets. Rounded edges strengthen parts by reducing stress concentrations. Fillets also improve material flow during printing, reducing the risk of defects. 4.2 Chamfers. Angled edges improve manufacturability, particularly in areas where surfaces meet. Chamfers are especially useful in parts requiring tight assembly tolerances. Simplify complex geometries. Intricate designs may look impressive but can create challenges in 3D printing, particularly in biomedical contexts where precision is paramount. 5.1 Segment large designs. Break down large or intricate models into smaller parts that can be assembled post-printing. This improves print accuracy and reduces failure rates. 5.2 Avoid unnecessary detail. Features smaller than the printer's resolution will not print accurately and may complicate the design unnecessarily. Test with prototyping. Prototyping is a crucial step in refining CAD designs and ensuring they perform as intended. 6.1 Iterative testing. Begin with low-resolution prints or smaller sections to validate key design features. Use these prototypes to identify issues before committing to final production. 6.2 Feedback loop. Analyze the prototype's performance and adjust the CAD model accordingly. This iterative process ensures the final product meets all requirements. Optimize for post-processing. Most biomedical 3D printed parts require post-processing to meet industry standards. Consider these needs during the design phase. 7.1 Surface finishing. Allow for polishing, sanding, or sterilization in your design. For example, extra material can be included where sanding will occur. 7.2 Assembly fit. For multi-component designs, account for dimensional changes caused by post-processing methods like heat treatment or polishing. Conclusion. Designing CAD models for 3D printing in healthcare requires precision and adherence to strict standards. Key tips include ensuring watertight geometry for accurate printing, integrating constraints like biocompatibility and manufacturability, and leveraging parametric modeling to optimize designs. These practices enhance functionality and efficiency for medical applications such as implants, prosthetics, and surgical guides.